To address the free space fragmentation and aggregation issues we mentioned in the previous morsel, the Linux kernel relies on two basic allocation mechanisms. The first one is called the buddy allocator, and the second one is called the slab allocator. The buddy allocator starts with some consecutive memory region that's free, that's of a size that's a power of 2. Whenever a request comes in, the allocator will subdivide this large area into smaller chunks such that every one of them is also a power of 2. And it will continue subdividing until it finds the smallest chunk that's of a size that's a power of 2 that can satisfy the request. For instance, in this figure, when the first request of 8 pages came in, the buddy allocator subdivided the region that was 64, the original area, first into 2 chunks of 32 pages. Then it subdivided one of these 32-page chunks into chunks that were 16 pages in each. Then it subdivided this 16-page chunk into chunks that were 8 pages each. And it turned out that this 8-page chunk satisfied the request that was for 8 pages, so that was great. Subsequently, another request for 8 pages came in, and then a request for 4 pages came in, and for that reason, this chunk of 8 pages was subdivided into 2 chunks of 4. Now, when this 8-page region is freed, there will be some fragmentation here. However, when the next 8-page region is freed, the algorithm will quickly be able to combine these two to produce a 16-page free space. So fragmentation still exists in the buddy allocator, but its benefits are that when a request is freed, it has a way to quickly find out how to aggregate data. When this allocation of 8 pages was freed, with the buddy allocator, it was very easy to figure out what is the start of the adjacent allocation. Where does the buddy of this 8-page region start? If we didn't have this information, if we didn't know that the adjacent region is also an 8-page region, we would have had to potentially scan all of these pages to determine which one is free and which one isn't, so as to figure out whether we can increase this free space to 9, 10, 11, 12, or some other number of pages. So the benefit of the buddy algorithm is that the aggregation of the free areas can be performed really well and really fast. The checking of what are the free areas in the system can further be propagated up the tree to check the buddies of this 16-page free area and then the buddy of the 32-page free area and so forth. The reason why these areas are the power of 2 is so that the addresses of each of the buddies differ only by 1 bit. This makes it easier to perform the necessary checks when combining or splitting chunks. The fact that allocations using the buddy algorithm have to be made in a granularity of a power of 2 means that there will be some internal fragmentation using the buddy allocator. This is particularly a problem because there are a lot of data structures that are common in the Linux kernel that are not of a size that's close to a power of 2. For instance, the task data structure, task struct, is 1.7K. To fix this issue, Linux also uses the slab allocator in the kernel. The allocator builds custom object caches on top of slabs. The slabs themselves represent contiguously allocated physical memory. When the kernel starts, it will pre-create caches for the different object types. For instance, it will have a cache for task struct or for the directory entry objects. Then, when an allocation comes for a particular object type, then it will go straight to the cache and it will use one of the elements in this cache. If none of the entries is available, then the kernel will create another slab and it will allocate an additional portion of contiguous physical memory to be managed by the slab allocator. The benefit of the slab allocator is that it avoids internal fragmentation. These entities that are allocated in the slab, they're of the exact same size as the common kernel objects. Also, external fragmentation is now really an issue. Even if we free objects in this object cache, future requests will be of a matching size and then they can be made to fit in these gaps. So the combination of the slab allocator and the buddy allocator that are used in the Linux kernel, these are really effective methods to deal with both the fragmentation and also the free memory management challenges that are present regarding memory management in operating systems.